A lot of calculus is based on the concept of limits, so it's important that we become really familiar with how limits work. In this video, we're going to go over some of the properties of limits. Let's start with these three basic properties. The first property is just saying that if you take the limit of a constant, it's just going to be that constant. Now, the next two properties are saying that if you take the limit of basic functions like these, you can use direct substitution to find the limit. In other words, you can just substitute c in for x, and that is going to give you the limit. All right, let's look at a few examples. If we want to take the limit of 3 as x approaches 2, the x approaches 2 part doesn't even really matter. The limit of a constant is just going to be that constant. Now, if I want to find the limit of x as x approaches -4, I can just do direct substitution, just plug in -4 for x, and the limit will be -4. If I want to find the limit of x squared as x approaches 2, again, I can just do direct substitution and substitute 2 in for x. So that's going to give us 2 squared, which of course is 4. So the limit is 4. All right, here are some properties of limits that you need to be familiar with. First of all, the scalar multiple property. If you have the limit of a function that's being multiplied by a constant, you can take the constant out front, and then you can just go ahead and take the limit of the function and then multiply by the constant afterwards. Now, these next few properties are really cool. Basically, if you have addition, subtraction, multiplication, or division, these properties tell us that we can take the limits of each part separately. So if I have the limit of something plus something, I can take the limit of each part separately and then add or subtract. If I have the limit of something times something, I can take the limit of each part separately and then multiply. If I have the limit of something divided by something, I can take the limit of each part separately and then divide. And then finally, there's the power rule that says if you have the limit of a function that has an exponent on it, you can take the limit of the function first and then apply the power afterwards. For problem number 2, let's find the limit of this polynomial using the properties that we just learned. Now, this is going to turn out to be the long way, but that's okay. We just want to practice using these properties. So the first thing I notice is that we have the limit of a sum. And we just learned that if you have the limit of a sum, you can calculate the limits separately and then add afterwards. So we can separate this by addition. So if we do that, this will become the limit as x approaches 2 of 4x squared plus the limit as x approaches 2 of 3. Now, let's not forget the basic limits that we learned right at the beginning of the lesson. For example, we learned that the limit of a constant is just a constant, and we learned that if we wanted to do the limit of x to the n power, we can just substitute the c in for x. So basically, this limit right here, I'm just going to substitute the 2 in for x. So this limit is going to be 2 squared. And I've still got the 4 out front. So I'm going to have 4 times 2 squared. And then, of course, the limit of this constant is just going to be the constant. So this limit right here is just going to be 3. So, in other words, we're going to wind up with 4 times 4 plus 3, which is going to be 16 plus 3, which is 19. So that is the limit as x approaches 2 of this polynomial. Now, I told you that we were really doing this the long way. Now, let me mention what the short way of finding the limit of a polynomial is. It's called direct substitution. And let's consider this polynomial to be the function f of x. All right, so what would happen if we just substituted the c value in for x? In other words, what would happen if we simply did f at 2? Well, this would turn out to be 4 times 2 squared plus 3, and that would be 4 times 4 plus 3. And this should be looking really familiar right now because it's right here. So, of course, this is going to give us 19, which is the same thing we got by sort of breaking this down using all of these properties. So this is going to turn out to work for any polynomial. So finding the limit of a polynomial function is super easy. You can just use direct substitution. So if I want to find the limit as x approaches 3 of this polynomial function, I can simply substitute 3 in for all of the x's, and that will be the limit. So the limit is going to be 2 times 3 squared plus 3 times 3 minus 5. So that'll be 2 times 9 plus 3 times 3 minus 5. So that'll be 18 plus 9 minus 5. And that's going to be 22. All right, so the limit of this function as x approaches 3 is 22. Let's talk about rational functions for a second. A rational function is a function where you have a polynomial in the numerator and another polynomial in the denominator. So what if I wanted to take the limit of this function, the limit of f of x? Well, if I wanted to take the limit as x approaches 2, could I just do direct substitution and substitute 2 in for all the x's like I did for the polynomial? Could I just do f at 2? Question mark. I'm hoping you're jumping out of your seat and saying, no, that would not work. Why would that be a problem? Well, the denominator, we have x minus 2. Imagine that I substituted a 2 in right here. Then I would have 2 minus 2, that would be 0. And you can't divide by 0, that would be undefined. So, if I wanted to find the limit as x approaches 2, I cannot use direct substitution. In future videos, we will learn techniques of how to find the limit of a function like this. What I want to say to you right now is any other value that I want to approach, I can find the limit. I can't find the limit as x approaches 2, but if I wanted to find the limit as x approaches 3, then I could do direct substitution. I could simply do f at 3. All right, you can do direct substitution on a rational function as long as the value that x is approaching does not cause the function to become undefined. So I could do direct substitution here, and this would turn out to be 24 over 1, which would simply be 24. So the bottom line is, if you have a rational function, you can still do direct substitution to find the limit as long as it's not a value that's going to cause the function to be undefined. Watch out for the zero denominator scenario. So again, if you want to find the limit of a rational function, you can use direct substitution as long as direct substitution does not cause a zero denominator. So looking at problem number 4, here's a rational function. I want to find the limit as x approaches 1. I want to use direct substitution, but I need to check, will it cause a zero denominator if I put a 1 right here? No, 1 plus 1 is 2, that's fine. The only problem would be if I wanted to find the limit as x approaches -1, then I'd have to use some other technique. But for this problem, I can simply do direct substitution. So I can just substitute 1 for all the x's. So this is going to be 1 squared plus 1 plus 2 over 1 plus 1. This is going to turn out to be, well, that's just 1, so that's just 4 over 2, which is 2. If you want to evaluate the limit of a trigonometric function, you can still use direct substitution as long as the value is defined. So if I want to find the limit of tangent of x as x approaches 0, I can just substitute 0 for x, and that's going to give me the tangent of 0. Now remember that tangent is sine over cosine, so this is sine of 0 over the cosine, not theta, over cosine 0. 0 radians is going to be right here at this spot. Remember that the sine is the y value on the unit circle. So this is the point 1, 0. So this is the sine, and the x value is the cosine. So sine over cosine. So the sine of 0 is 0, and the cosine of 0 is 1. So the tangent of 0 is 0, and that is the limit of the function. Look at part B. I have the limit of a product. So we learned earlier that we can separate multiplication into two separate limits. So this is going to be the same thing. You know what? I think I'm just going to scroll down a little bit. This is going to be the same thing as the limit as x approaches pi of x times the limit as x approaches pi of cosine x. So we've learned that we can just use direct substitution in both of these cases. So if I substitute pi for x right here, I'm just going to get pi right away. And if I substitute pi in for x right here, then that's going to give me the cosine of pi. Now remember, okay, pi is right here. So this is what we're talking about. And cosine is the x value. So the cosine of pi is going to be -1. So we're just going to have pi times -1, which is -pi. For part C, we have the limit of a function that's being raised to a power. So we learned that one of the properties is we can start by taking the limit of the function first. So if I can do the limit as x approaches 0 of sine x, and then I can do the power afterwards. Okay, so we've learned that we can take the limit of a trig function by direct substitution. So I can just substitute 0 in for x. So this will become the sine of 0, and then I'm just going to have to square that afterwards. And remember that the sign of 0, this is 0 radians right here. Sine is the y value. The y value is 0. So the sine of 0 is 0. So we wind up with 0 squared, which of course is 0. Now let's talk about how you find the limit of a composite function. And of course, a composite function is where you have a function inside of another function. And it turns out, if you take the limit of a composite function, you're allowed to take the limit of the inner function first, and then apply the outer function to that limit, as long as you don't get any undefined values along the way. So for example 6, part A, we're going to find the limit as x approaches 0 of the square root of x squared plus 4. Hopefully you can see that this is a composite function. The inner function is x squared plus 4, and then the square root is the outer function. I'm going to colorize this to make it easier to follow what I'm doing. So I have the limit as x approaches 0. And then the outer function is the square root part. And the inner function is the x squared plus 4 part. So it turns out that we are allowed to take the limit of the inner function first and then apply the outer function. So that means that in this case, we are allowed to start by taking the limit as x approaches 0 of the inner function, x squared plus 4. We can do that first, and then we will apply the outer function, the square root, afterwards. Whoops, I forgot the as x approaches 0 part. Now, we have learned that if you want to find the limit of a polynomial function, you can just do a little direct substitution. So if I want to evaluate this limit, I'm just going to substitute in 0 for x. So of course that's just going to give us 0 squared plus 4. So this is going to be the limit, and that's going to give us 4. And then we can apply the outer function afterwards by taking the square root, and of course that will be 2. All right, so the limit of the original function is 2. Let's do one more. The limit as x approaches 3 of the cube root of 2x squared minus 10. Again, this is a composite function where 2x squared minus 10 is the inner function and the cube root is the outer function. So I'm going to go ahead and colorize it so you can follow me very easily. So first, we have the limit as x approaches 3. The outer function is the cube root, and the inner function is the 2x squared minus 10. We have learned that when you have a composite function, you are allowed to take the limit of the inner function first. So we can go ahead and take the limit as x approaches 3 of the inner function, 2x squared minus 10. We can do that first, and then afterwards we will apply the outer function, which is the cube root. And again, if you want to find the limit of a polynomial function, you can use direct substitution. So we are really just going to substitute 3 in for x. So we're going to have the cube root of, and so this is going to be 2 times 3 squared minus 10. All right, well, 3 squared is 9. 2 times 9 is 18. And 18 minus 10 is 8. And then, of course, if we take the cube root of 8, that's just going to be 2.